Hello everyone, this is Sagar Pandey from VIT University. So today I will be looking upon the course called Nand To Tetris. So Nand To Tetris is basically a software that is used to create a fully functional modern computer on which we will be able to play the Tetris game. And the specialty would be that it will only be made with basic logic gates like the AND gate and the NAND gate and the NOR gate. So for downloading the software, you need to go to the official website of Nand To Tetris. We see here. Just go to the software section. Yeah, so this link is clickable, and using this it will download a zip file. I have already downloaded the zip file and will be running the same software. It's here. Unzipping this file will give you Nand To Tetris software, and it will contain 3 subfolders: the projects and the tools. We are here basically to deal with these 2 folders. So you will go to the tools option, and the first 4 modules of Nand To Tetris are the hardware simulation. So this Windows bash file is runnable. We open it. Yeah, so this is basically the interface of Nand To Tetris. So now let me brief you some of the functionalities and the buttons. So this is the load chip option. So what we exactly do in Nand To Tetris is like we try to mimic the properties of the actual hardware by writing the codes to simulate the functionality of that chip or the gate or the complete IC. So these are the input pins, the input variables, and we can change the values of these, and depending upon the value of these input variables we have the output variable. And this HDL stands for the hardware definition language. This the code that we actually write for the functionality, for implementing the functionality of the gate, is actually displayed over here. So this button is the load chip option. With this we load a code of a particular chip onto this simulator tool. So in this video we will be discussing upon the functionalities of the XOR gate and the multiplexer, specifically the 2-in-1 multiplexer, and the half adder and the full adder. So let's first load the XOR gate. So for the XOR gate you need to open the project file. In this 00 we have the XOR. You can see XOR.htl. HTL stands for hardware definition language. So we open it. Yeah, here we go. So we have this code loaded in the HTL section, and this input variables are A and B, and the value of these can be altered relatively according to our wish. These are the output pins, and this is the internal pins. So some of you may be wondering that what is the use of these internal pins, like what's the use of A and B and A or B. So let me just brief you over this. Yeah, so internally we all know that the XOR gate is mapped into like this expression. So it's A plus B, that is A or B, that's A or B over here, and that's multiplied by A bar plus B bar. That's basically the NAND operation. So it's A NAND B, and the output pin is the multiplication of A NAND B. So this is the functionality of the XOR gate. Now we test that the code is actually working or not according to the truth table provided. So initially it's launched with the 00 operation, and if we change the value of 0A as 1 and enter, see, now we need to update the value of output pin so that it's updated with the inputs, new inputs. So we press on the eval option. Yeah, we see the output pin is updated to 1. Now we check that is the output correct or not. Now for A is 1 and B as 0, the output is 1. Yeah, so correct. Now let's check with another test case. Let's go with 1 and again evaluate. It's 0. Yeah, so it's 1 1 and 0. So the functionality of the XOR gate is implemented. Next we go on to like another, say, next project, and let's go mux. So it's basically 2-in-1 mux, as we have 2 input variables A and B and 1 selection line, that's SEL. and the output pins are out, and these are the internal pins, and this is the code for the 2-in-1 mux. So So now let's check the functionality of the mux code we have written, that is the 2 into 1 mux. So initially it's launched with the 000 option. So now we will be updating the let's take this one 010. That's we need to update the b as 1 and press enter and evaluate. So the output is 0. So it's 0, 1 and 0 and the output comes 0, so it's verified. Now let's check with 111 option and then evaluate it. So it should come as 1. Now it's 0, so it gets updated to 1. So the code for the mux is running correctly. Now let's move on to the let's say the half adder. We have in the code for half adder. It's loaded here. So this is the code for the half adder, and we have the input variables as a and b. So this is the circuit diagram and the truth table for the half adder. A and B are the inputs, and the sum and the carry are the outputs. And there is no internal pins needed because of the gates are simple. So it launched initially with the 00 setting. We need to so for checking we need to update A with 1 and then just update the val. And yeah, then a 1 plus 0 gives sum as 1 and the carry as 0. Now let's update b with 1 and then again evaluate. So yeah, so the carry goes 1 and the sum goes 0, so it's verified by this particular test case. So the functionality of the half adder is working correctly. So the last one we need to go with these 4 modules is, let's say, the full adder. Yeah. So the full adder has the circuit diagram like this, and this is the truth table for the full adder. So initially is launched with the 000 settings, and the outputs and output of are sum and carry. So the C in is in this table is actually the C variable, and the carry is the C out variable, and the S stands for the sum. So now if we update A with 1 and then try to check the code, so it gives A plus B plus C in gives sum as 1 and C out, that is carry, as 0. So it's verified in here with this 100 gives C out as carry as 0 and sum as 1. Now let's keep all of them as 1 and then evaluate the result. So the sum is also 1 and the carry is also 1 because 111 gives 1 with carry 1. So it's verified by the last test case of this table. That's 111 gives sum as 1 and carry is also 1. So these were the implementation of the XOR, the multiplexer, and the half adder and the full adder. So these consist of the first 4 modules for NAND to Tetris. So here I'm wrapping up the video, and thank you for watching.